Well, hello everybody. Tonight I'm been playing with my uh, Manta motor, getting it all sized up, and just wanted to show you my progress on it. The It's all about the prop and it's all about torque, okay, and the torque and RPM. Uh, this motor right here, this design, this Outrunner design, it's 36 slots with 48 poles. And it's one of the first motors I started working on. It clued me in on a lot of things. And it was the first step of the Mogen experience 3 years ago before I converted it to what it is today. But I learned so much because that was 14 pounds of motor. Each leg on it was 100 volts, and the had incredible torque. And that's really when I started learning reluctance motors. That particular style motor right there was a big learning curve for me. Lots of torque, and the head engineers tell me, no, you can't ever get that over 4,000 RPM. That's you can, okay. There's a secret to it, and anybody that comes back and tells me the secret of it has been there. But I call it the pumpkin seed, and when you push it out of the field, it speeds up like a son of a gun, and I found that out accidentally on the bench, playing with it, and built a device to speed it up, and had a lot of fun with it. So, want to move into what we're doing. The motor that we're working with, 16,049 is as fast as we really want to run it. I mean, we want to be capable of running it at that. The thing about motors, generators, and everything in that area is you want to find the sweet spot is usually 80% less than what it's rated at. Okay. And so if you're running a motor or a generator, it's the most efficient running it at about 80% is far as your return on investment. If you're employing gasoline, diesel into it, it works pretty much the same with motors as well. So you want a high service factor, but you want the foot pounds of torque keyed back to your RPM. And so if you're really designing this motor correctly, even though we want to only spin the prop at about 16,000 RPM maximum, okay, you want to keep that in mind. So the 4.5 pounds of torque at 16,000 RPM gives you right at 13.7091 horsepower, which is right on the money, and that's right in that area that we're working with. Now, want to get into motor designs, and whenever you add metal to a motor, the laminates, just like that little motor right there has laminates and coils. The metal has hysteresis. It has memory. That's what that means. And you can put less copper in it, okay, and but it's going to cog. Okay, that cog does turn into torque. The what I want to show you is that you can use aluminum, okay, for your housing, and it becomes all about mass and drag, and you can actually wire your copper in, and for the size motor, and I'll show you how I got there that I'm developing, it works out to about 4.5 pounds of copper in it. Okay. Copper right now in the commodities market, you know, if you buy commodities, you can buy copper wire for about $4 a pound. Okay, I mean that's the real truth of it. You know, you go to the retail store and they sell it for $10 a half a pound. Okay, there's no cent in markup, and that's just the way our system works. But if you're designing something to be mass produced, and this unit that I'm building will have other uses as well. You know, it's not. You could use it on model aircraft, but I'm building it to put on an aircraft, and I want it to run without any maintenance to it. Okay, when I design it, be well designed, and of course the first ones we won't have made by machines. You know, to be custom crafted, and we'll test out in the lab and make sure everything works okay. But once you're set up and you go to the correct motor shop, they can wind it and have all the windings look perfect, everything to detail, and so then it becomes a manufacturing prototype. But I just wanted to show you that my motor is not going to have any cogs to it. Doesn't need to, because it's spinning up so fast. And with the type, it's going to be a permanent magnet motor. But with the type magnets that I'm using in it, because my target weight is right at 6 pounds total, including the prop, including the adjustable prop feature that I'm having on it. So the 6 pounds is my target. I want to come in right at 6 pounds, and that's about what it's going to take to build this particular unit. But it won't have any. It won't cog, so it's not going to have a whole lot of torque. It'll have good torque. Don't get me wrong, but the way I've designed it, with the no load, as it spins up and gets to RPM, that's the way this will spin up. Okay. I may change my mind on that. If I do, then it's no problem. The very interesting thing about 20 gauge wire is that you can bend it really sharply, and if you do that one lap at a time, okay, you can do things, okay. One strand of 20 gauge magnet wire, or motor winding wire, is good to about 1.5 amps by itself. Now there's caveats to all that, but that's just kind of a design thing that you can use with number 20 gauge wire. Okay. In these type motors, the size wire that it ends up being is like a 10 gauge wire. But the problem is, if you took a 10 gauge solid strand, or this is stranded wire, it's very hard to bend, and you can't get it won't keep its shape, and you can't form it. And so I'll get into a little bit more of that with winding, and that's the way these work. These have very few actual coils, if you will, okay? But you have a big enough flow by putting enough wires together, single stranded, and coming to end at your terminations to get the size wiring that you need to carry the amps. Okay, so the this size wire, when you wrap it up, uh, uh, can handle right at 90 amps. Okay, in a short configuration. Now you start getting over a few feet, and it really mounts up for there. But these type motors for propulsion, that's pretty much the theory, is that you're using smaller magnet wire, but you're using many strands to make one strand that's what you need to do it. And then the for these type permanent magnet motors, when you're spinning up in 16,000 RPM range, it works out so many turns per volt that you're actually driving it at. And so I run my motors at much higher voltage than like an RC motor runs at. And I'll get into that later on, why I do it that way. The next step is you got to figure out the size of your package. So we already, working the scale, and I'm working with a 15-inch prop diameter, and we've already figured out all the things on that. Now, what we got to do is find the actual packaging, and messing around. That's the actual packaging, and as you can see, we're getting pretty close to what the package is all going to fit in. Okay, so we got length and width, and we can do more calculation with how to wrap the wires into the unit, the size of the rotor, the size of the stators, and we can figure out if we want to make it an outrunner or an end runner. And so there's advantages to both. Again, this is going to be able to run for long periods of time, and so it's going to be cooled. It's going to be liquid cooled. And so there's different ways you can use oils and other things to cool with besides water. And oil works really good for pumping through. So there's going to be a cooling system added to this system to keep it cool, because when you start putting out that much torque in a small package like that, to do the same thing that we're doing normally with electric motor on mains power, about 3 pounds per horsepower is about the design rate, but we're not using near the metal as far as the steel in it. We're opting for copper and aluminum for mass. The steel robs power and gets hot, and it weighs more. Okay, so that's now we know the size package. We're getting scale to it. We can put our shapes into that for the suction side of it. Pitch control, I've already got that worked out, and I'll be showing that to you later on. Okay. But just going through, this is a typical type motor. Now I'm showing it in a blown up fashion, but this is a motor that puts out, operates at 20K in the 20,000 watts. Okay, and typically they run these type motors at 48 volts, 50 volts, 60 volts, in that range. Okay, This motor, even though you see all these windings in here, the actual turns is only 2.5 turns, okay, uh, per section. And so that's what I was showing you there. If I end up needing a little more torque, then I can go with the permanent magnets, and you can swap this around either way, and that's the configuration, the winding to be done on that. So I know how to calculate all that, no problem. The for sizing, the got a piece of 1.5 PVC, and so the you can see how it's all coming to scale in the 3D model section of it. The originally, when I was working with this and making up my models, this actually has the model, excuse me, has 10 magnets and 9 stators, and with the timing and everything, you can see how they run through there. Now that has too much mass in that configuration to run at 16,000 RPM the way that I'm going to do it. Be more, if I go with metal in the design, if I do need the torque after I put the prop on it and load it up, then this will be the next step to go. And what I want to do is put as least amount of cogging in there as I need to get the torque where I need to spin the prop and get it up to speed that I want to run it. So a little bit of experimentation to go there. Wanted to give to show you how you can double the wire up to the size to handle the amps, and then in a long motor configuration, the way that the windings would actually fit into it. Okay, and they're actually epoxied into place, and the wire is formed, and the clearances from the rotor and the stator is in that type configuration. Okay, that's the reason you use multiple wires instead of one big wire. Okay, and that's really getting the sizing figured out, which is in the shapes, bringing it up to 3D. That's the way I do it, and that's the way I've been doing it for years and years and years. I find something that looks about right and it fits within the angles and everything that I'm working with, and figure out the size of the package that I got to fill up, calculate what I need in there, and then the fun starts when I get to building that up. So getting ready to make my molds up, and I'll show you as that goes along and progresses. Hope you're having fun. Hope you're having a happy new year. We're having a blast taking down all the stuff from Christmas and getting it all put up for next year. And we're expecting some snow tonight. So, but I hope you enjoyed my presentation. I hope it helped you, and hope you have things that you're wanting to proceed with your projects besides your work. So we'll see you next trip.